First, I want to thank the organizers for inviting me here. Of course, I encourage lots of questions during the talk. So the title is Complex Phases in Systems with Competing Interactions, or in the title is for Repulsive and Attractive Interactions, Implications for Vortex Matter in Charge Ordering Systems. But I also want to emphasize that many of the same things I'm going to be talking about should also be possible for systems with just repulsive interactions, provided that you have some kind of step in your function so that if you take the Fourier transform of that potential, if you have a negative mode, that will give you also an effective, you'll get the same kind of pattern received with the attraction. And this might mean that there's a lot more ways to see these kinds of systems.
Are you talking about fermions or bosons?
Okay, well, so neither at the point. At this point, it's actually classical matter.
Oh.
Okay, so.
Okay.
So I'll thank my the people who have been working with me over the years on this: Cynthia Olson, Reichhardt, Ivor Martin, Christian Batista, and Alan Bishop at Los Alamos. I should also add, just very recently, Lev Boloveski has given us a few ideas as well to look at. And a quick introduction, just the general idea of pattern formation in systems you have competing interactions. The background of this, how do you get these patterns, and so on. And it has lots of implications for soft matter systems, and more recently thing, these ideas are starting to be applied to hard condensed matter systems. And I'll mention how you might be able to get these phases. And the particularly interesting thing about these systems is that despite the interaction potentials that you can use a lot of different kinds, if they have certain generic features, you always see the same sequence of phases that look very similar, despite systems that have only very short range interactions versus systems with long range interactions. So what do those phases look like, and what are the transitions between these phases, and how do they melt if you have thermal effects, and they have interesting melting transitions? They might have a multi-stage melting transition. Basically, we get stripes, bumps, and bubbles. Of course, in a lot of real systems, particularly hard condensed matter systems, they're not going to be in a vacuum. They're going to be on some sort of disordered substrate, a quench disorder, and it has a tendency to break these patterns up. So you want to know, how could you try to get to the underlying pattern even though you have quench disorder? One example might be depinning the system or shaking it back and forth, and so on. There's also some implications for hysteresis. Generally, these systems are exhibit a lot more hysteresis than so uniform. So we'll keep the introduction very general. So pattern formation is, you see in lots of systems. So this is just starting from sort of the highest things. For example, biological systems, you see these patterns. And remarkably, the patterns on this fish don't look that different from the patterns you'll see in, say, magnetic garnet system. This is a chemical reaction going on here, two different types of chemicals. This is wind blowing over sand, and over time you almost get waves forming, but they're not moving waves, they're just static waves. And this is a pattern on a comb snail, which I think is the most poisonous animal there is. So close to the condensed matter systems, is again you start to see these similar patterns. And here's an example of a diblock copolymer where you have two phases. They phase separate. They don't have just one portion on one side or another. They mix, but they mix in this almost a fingerprint type pattern. A very similar pattern is seen for a different system. This is Rayleigh-Bernard convection, where you have some fluid that you heat up, and you have some of the hot water going up that cools down, comes back down, so the white spots would be where the hot water is coming up, and then black spots is where it's going down. And you see you get a very similar type of pattern. I don't have a picture of this, but most people are familiar with magnetic garnets. If you have a magnet with two different directions of the field, you can have these phases look very much like this. Other kind of pattern here is electroconvection, electromigration, where you have current flowing through a material, and over time, the flow of the electrons actually drags some of the material with it, but it ends up forming these patterns, and this kind of process is important to the breakdown of certain electronics. Okay, so going closer to the systems that we want to look at in this matter, is suppose we have systems with repulsive interactions. I'll emphasize some of the smooth repulsive interactions. So this is a colloidal lattice, which is basically a macro version of a Wigner crystal. These are solid particles in water, essentially, but they have a charge on them. But because they're in solution, there's some screening, so they essentially interact via Euclid interaction. And that forms this nice triangular lattice. And that this ordering reduces the interaction potential as much as possible. And this picture is just taken with a video camera. You can turn up the temperature and watch it melt and so on. Down here is a picture of a superconducting vortex lattice. And the standard, depending on the type of vortex, but you will have a nice repulsion with a isotropic repulsion with a Bessel function. And that, again, produces this nice triangular lattice that's uniform. Now, of course, there's examples where you can get some nodes in the repulsion, so it's a little more repulsive in certain directions than others, and that will generally distort the system, maybe make it square or rectangular, but it will not really break up into two length scales. It will pretty much be uniform. So you can also make systems, particularly soft matter systems, where you can sort of tailor the interactions, where you have, say, some charge, screen charge, so that means it's going to certainly be repulsive on short range, but you can have some long range attraction. And here's an example of a system with some particles that are charged. They have it on a water-oil interface, so it's such that they cause a divot in the surface, which creates this long-range stress field. And ideally, if you have another particle here with this divot, by coming together and sharing the divot, that's less energy than having two divots apart. So it's sort of like what they call the Cheerio effect. In cereal, you put some solid objects in your milk, and over time they come and stick together. Right? And so what they were studying here is that you can get these cluster phases. So they generally come in, but they can't completely collapse. But they find if you were to you do this over and over again, there's certain clusters they call magic clusters, such as if you have 37 particles, provided that they're all the same size, same charge, it can form this hexagonal subpacking.
So what are the particles in that particular case? Because no, the second from the left.
Oh, this?
No, from the left.
These are the same thing, right?
Oh,
so the colloidal particles.
Okay, I see.
So they're just...
So what the bonds there are not simply real particle, it's simply a bond. You show where the bond is, right?
Oh, yeah. So in this picture here, this is basically a Wigner site cell construction. So at the center of each guy is the particle. Okay. And then you just draw out to the nearest neighbor. So he has 6 nearest neighbors, right? Over here, you have the guy sitting in the center has 5 nearest neighbors. So to get the particles to be, the system wants to be triangular as possible, but it doesn't want to be round because that would introduce defects on the edge, and those cost energy. So they can go through all these numbers, and you get these magic numbers coming out.
You can make a regular lattice with 5 neighbors like that?
A regular lattice? No. I mean, that's just your one guy here, right? In the center, he's 5. So it's like a disclination. So so this costs energy. So this guy is less happy than this guy. And they actually do some experiments where they try to break them up.
Okay, I see.
So you can do something that you can increase. So once they create these substructures, you can test the stability by, for instance, changing the charge. You can make it less screened by changing the salt. You remove the salt or the stuff that would screen it. So the thing wants to break up, right? Because it doesn't. Eventually it's become unstable. And if it's in this configuration, it will like to stay in that configuration longer than this one. And so n equals 70, so there's some defects, 85. And you mentioned 13 the other day. I believe that's one that forms a nice sub-hexagonal pattern. And then here they show that you can have mixtures, and they try to make these things, they call them colloidal molecules.
Is it two kinds of particles or some bigger?
Yeah, these are two kinds of, well, no, it's just, these are a bigger version of it. Right? And they're trying to say that you can get sort of magic numbers as well, that the big guy has a tendency to go towards the center, right? And that's because he makes the biggest divot. Okay, so keep this in mind because this system supposedly has the long range attraction. So what states do you see? You see a cluster, a single cluster.
Again, small ones emerge into big one, or they have a short range repulsion.
There's a short range repulsion, right? Yeah,
so
exactly. So this model is short range repulsion because they're charged. Of course, if they get too close, they can hit each other, right? But they're charged. But that charge is screened because it's just a solution. But there's also this additional long range attraction, which goes almost like somewhat like one of ours.
So the big one is not a sum of two small ones.
No. The big one is just a bigger particle. So these particles they're real solid objects. They can't like a superconductor, like vortices can actually merge and form a two finite vortex. These objects they just hit each other. So now going to hard condensed matter systems, is that there's been, is Jan Zan in here yet?
I haven't seen him.
Oh, because so he'll want to go, he came up with it first and just, yeah, okay. So he did it all first, but, anyway, so the idea, so similar ideas start to come out in hard condensed matter, or where you can get a system where you have long range repulsion and some kind of short range attraction. And some of the ideas we're talking about in the cuprates, or where you have your dope in some kind of insulator phase where you have spin degrees of freedom. You put a hole in there, that's a charged object, it's repulsive, but it distorts the spins around it. In the next picture I'll show you that again, it's not that different from this thing, because this costs energy. If you put another one down, they can share their divot, and this time they share their spin distortion, and that will lower the energy. Now, the quantum Hall effect, these are the stripes I talk about, the quantum Hall effects. This is actually an example of what I mentioned earlier, is a system with just repulsive interactions that can give rise to stripe and clump phases. And I'll say a little more later about that. But just to emphasize that these ideas of systems with some kind of effective competing interactions or different length scales will give rise to pattern formation. So here's, so as I said, even though stripes have gained a lot of appeal from the theorists Kivelson, Fradkin, for both quantum Hall and superconductors, Misha Fogler and Boris Schlotsky and Kulikov then talked about the version for short density waves for quantum Hall systems, and I should also add Chalker and Meisner also around the same time had these ideas. But earlier, Jan Zan and collaborators have also suggested something like this can happen, and really they got the idea actually from the physics of nuclei, and I'll mention that later on. So here's an example of this antiferromagnetic system. You put a hole here and a hole here. So of course the repulsion, they want to get as far apart from each other. But suppose this guy distorts 4 spins, this guy distorts 4 spins, and that costs energy. But by bringing them together, they only distort 6 spins. So you save a little energy by bringing them together, even though you have a problem with the repulsion here. So if you start adding a bunch of them in there, you can ask, well, what kind of thing will they form? Because they just don't want to minimize the repulsion, but they also want to try to minimize the spin thing, which isn't effective attraction. So a lot of the ideas right away you mentioned is you can have crystal phases, but these things should also form stripe phases. The stripes can come out all sorts of of shapes and sizes. For instance, if they're all aligned one direction, but liquid light, you get the symmetric phase, which is a liquid crystal nomenclature. If it's more generally not aligned, you start getting these dislocation-like pairs being created. You get a pneumatic phase. On the other hand, you can get something that's stripe-like, but it's isotropic, but it's not isotropic like the crystal because you have these labyrinth-type phases. And of course, evidence for these could be anisotropic transport, imaging, and so on. I'll just say this more, to go through this a little bit more quickly, is, of course, there's been a lot of talk, perhaps in high-temperature superconductors, these things are going on. And this is actually somewhat older, but here they don't necessarily see stripes, they see something like a checkerboard. This is a famous image. I think more recently there was a recent paper about pneumatic ordering. I'm going to withhold all judgment on this. If anyone has strong opinions, let me know.
You should have pictures of tartans there too.
Of what?
Tartans. Scottish tartans.
Portrons?
Tartan.
Portrons.
The cloth.
Oh, tweed. I know what you're saying, yeah. Yeah, this is sort of like, it looks like sort of like a tweed pattern, right? Okay, so now this was for these hard condensed matter systems. But more recently, there's been an idea that perhaps certain models, superconductivity or vortex matter, can also exhibit things that are significantly different from the standard hyperclassical vortex size. One of these is the 1.5 superconductor, and I see Alex is already looking edgy. What? Anyway, but I also should add, I believe Professor Vincent Liu there was a paper I thought I saw you some years ago where you had maybe in a vortex lattice and certain Bose-Einstein condensates could have more complicated interactions. So I think, well, we could say more that maybe there's a way to sort of to tailor the vortex interaction in certain systems, and you will end up getting phases that look like these structures. So, of course, this was depending on there's some controversy with this, but I'll start off with my history. Is that you can have a system where they took a type 1 superconductor, you have an insulating layer, and you put type 2 superconductor, you then apply a magnetic field, and so the type 2 vortices, of course, they'll have the regular repulsive interaction and won't be uniform. However, your type 1 vortices will have, they want to form this single phase, so that's an attractive interaction. So in essence, you can have a system that has short range repulsion, but longer range attraction. I believe that's the correct way of stating it. Okay. So, so now, to sort of agree with Alex, though, there's some weird problems with that, if that's true. Because if you really have a system like that, do you expect stripes and clumps and bubbles? Well, I don't know, because earlier you saw that, generically, if you have long range attraction, why won't it just collapse? So that's some issues there. But you also have, you could have points disorder. But anyway, so here's an example of, they propose you can have a system of vortices with competing interactions, so you will get something different than our Russell vortex size. And one example where this system could be realized is magnesium boron, what's a 2-band superconductor, and you assume one band is type 1, and the other band is type 2. And then here's a low field image of the system, and you get these funny sort of stripe phase. Over here, I believe, is niobium, and then you get the more uniform vortex size. The same group then did a simulation, which I don't understand.
I think in the second their paper they call it multi-fit. So the first paper they call it simulation. I don't understand how this thing can appear in simulation.
Right. Anyways, but you could say that if you do this simulation, this is just the pure repulsive, the standard vortex interaction. You get this nice, you start to get the uniform lattice. But then they add long range attraction. But the thing is, they never give you the pair interaction in the paper, right?
So is it 49 micron? Is it?
Yeah,
See, right?
the length scale. I know these things are pretty far apart, right?
Yeah,
Here's
40.
these are micrometers.
40 microns.
Yeah.
40 microns.
Right.
Wow.
So that tells you something kind of funny right there. But anyways, so they see these patterns. So the point is, there's some interest that if you have something beyond just sort of smooth repulsion in these vortex systems, you can get some kind of pattern formation. But there's some controversy. All right. So, but now I want to say mention that you don't need actual attraction put in by hand. That you can have a system with just repulsion that will give rise to these patterns. And here's an example of one of these systems. These are just again a classical simulation. This is motivated by certain colloidal systems where you have a hard colloid, which is not charged at all. It's just a hard sphere, and then around it you could have some corona of polymers, which they can interpenetrate each other, but it ends at a certain point. So if two particles are further apart, they don't feel each other at all until they get close enough that the coronas can start interacting, and they will have some sort of energy cost. And eventually, if you push them hard, close enough together, they just stop. So here's the interaction potential for this system. It has a hard wall. It has just a constant energy as you go in here. And then as you go away from that, it's just flat. That's it. So it's purely repulsive. What you see in this system is you see pattern formation.
What's the average separation there between particles?
The average separate,
In comparison with the radii, the sigma 1, sigma 0.
So a good guess would be, so these guys, right, basically are at this length scale, and the average length scale here is just a little bit beyond that, right? I'll go into a little more, so there's certain two length scales that always arise. One is this length scale, and one is the length scale just slightly beyond that.
So what happens if you take like a smooth function? Can you change anything?
Well, okay, that's a good question. So if you take a smooth function, right, that changes stuff.
Right, but
Hexagonal.
it's like exponential, for example. Instead of a step, you take two exponential.
So if you just have a step and you
No,
take
the hardcore and exponential.
an exponential. No, that's fine too. So the other people have looked at stuff. So you just need to have something. So if you take the Fourier transform of this, you'll get a negative mode, right? So the real key to get the pattern formation is this part, right? And then you want another part so that to keep them from collapsing, right? So if you have an exponential, that's fine too, right? In fact, there are certain, you can take a model of this thing and it doesn't have a hard core. You can just say it's a fuzzy ball of polymers that you can in fact collapse on each other. They call those soft core chromates. And that works as well. But this is sort of the easiest version to understand. And so here's an example. So if you're low density, this is a function of density. So if you're at low density, where the particles are beyond...
Is the same interaction as before?
Same interaction, right? So if you're at low density, so the average spacing of the particles is always
bigger than sigma
bigger
1.
than that. You just get a liquid, it's just a liquid. So then you increase the density, and you just get to right around the point when they start, the first length scale comes into play, the longer length scale, and then you get a crystal. But then you go further than that, then you start seeing dimerization and trimerization. And then further, you get the stripes, and further still,
What is the trimer? Can you show trimer?
So well, it's not a phase really. If you look at this, it's not quite ordered, but you see there's a tendency for pairs or to come in there, right? Maybe not so much trimers. So what's going on is that by forming, if they let them uniformly come in, right? If they form that last phase. If you just increase the density, all the particles would suddenly move into this energy region. So you have a big jump increase in energy. But if they say, okay, I don't want to do that, I can lower the average lattice constant by just having a few guys come in here and everyone else staying out here, right? Then I can keep the energy lower. And once they're in here, right, this part here, if they move all the way to the edge here, they'll also reduce their corona will be moved in with it.
So if for example, I'm in this stripe phase, but I turn thermal fluctuations, will it melt back to the crystal?
That is an excellent question, right? I believe that's true, right? We have some evidence that happens. And this would be a particularly good system to see it, but we haven't really studied it in full. There's something you will notice right away about this system, right? Is that they don't have, it has a tendency to not order that well. It's very metastable. But there should be this temperature-induced phase transition. So that's a great question. I think that we're pretty sure that happens, but so yeah. So you see what's happening here is that they instead of getting this whole crystal, this uniform phase more dense, where everyone starts to overlap in the corona, they go, okay, we'll just have a few guys go in there and dimerize, and then we'll keep a lot of extra guys out of those crystals. So that's actually lower energy. And then as you increase the density, this is essentially what keeps happening. And eventually, though, if the density is high enough, you have to go back to a phase that looks like this, because then it's just like packing in hard spheres. So you go back to a uniform phase. So here's the general sequence that these guys are seeing. You start off uniform, you go to clumpy stuff, you go to striped stuff, you go to more clumpy stuff, and then you go to uniform. So keep that in mind. So here's another version of this. Other people have studied it.
What determines the long range?
There's no long range interaction.
No, I know, but if I look at the image D there,
Yeah.
you see there is a certain length scale there, which is about.
Yeah. So that length scale. See,
Yeah.
So this length scale here.
No, that one is clear, you see, but I go
Yeah.
to D.
D.
D, yeah.
So
you see,
this length scale. So you see, there's two length scales, right? This other length scale, the longer one, is always the longer range.
yeah, no, that I understand, but I'm
Right.
looking, you see along the
Like the size of the
yeah, the size of the line, you see, roughly, you see,
Sort of
it's
a
small.
persistence length in the stripes.
Oh yeah. So that is okay. That's another good question. Is this doesn't have long range order, but in principle, it should, right? In fact, so this simulation is this parameter is the same. So if you wait longer and longer, right? Because every time there's a bend in there, it costs energy. Is that the lowest thing will be a stripe phase.
Why
But-
does a bend cost energy? In
Because
this system,
so
it
imagine
should
that
not.
you bend this over, right? Some of the coronas will start overlapping.
No, if you don't bend too much, you see, it shouldn't have any effect there.
Right. So what you're getting to a point is that, in principle, in the two-dimensional version of these systems, these stripes, you don't see ordered stripes. You see domains. Now, what exactly accounts for the length scale domain?
Mhm.
That I'm not sure. It's probably in annealing time. But this is another open question because a lot of these two-dimensional striped electron systems, they see anisotropic transport, so they assume stripes. But why does the stripe choose this direction when it should just break up into domains in all sorts of directions? Something has, so there might be some sort of symmetry there.
So is there any size dependence, for example, on the picture A?
Probably there is.
The
yeah.
size of these clusters,
Yeah,
is it
probably.
scale like the sample size?
So which cluster, are you saying?
Yeah, the big one, the
Oh,
biggest one.
the big clusters?
Yeah, like these guys. If I increase
Yeah.
the size by a factor of 3, would the cluster also increase by a factor of 2?
Yeah, probably depends
Yeah.
on the annealing.
Yeah,
No, they
yeah,
don't
'cause
have thermal
Ah, yes,
fluctuation.
you
it-
will.
like I said, these are
Yeah.
metastable crystals, right?
It's probably non-equilibrium.
Exactly. So that's another thing, is even in all these simulations that people are doing in this class of system, it gets hard to get to the ground states.
Yeah.
So there's some other people who use entirely different approach to this, rather than a Monte Carlo simulation. They use some optimization procedures. And then you can get completely ordered crystalline states. But in practice, when you do the simulation, you don't see them.
Okay.
Okay, so here's another group simulation, and you can see these phases, and theirs a little bit more ordered than the ones we saw before, because they actually have a longer range. In other words, they did the exact same model, but they made this much longer. And you can see this well-defined cluster crystals, but you can see they're not ordered in there. In principle, you could say it should be the same number of particles in every cluster then forms a triangular lattice, because you don't quite see it. So you have your clusters, your stripes, and then an anti-clump state, and eventually high enough density, it will go uniform.
Can I ask a question here? So now, if you, I think you see it was the question asked before. If I'll change this interaction to a repulsive Yukawa, for example, which have the same radius as sigma 1.
This one.
Yeah. So put everything a repulsive Yukawa all the way.
Oh, all just a pure repulsive?
Yeah. So
no step at all.
no step at all.
Okay, then you get a crystal. So
you get the hexagonal one and nothing else.
This is.
Yeah.
This is
So
just
and
a-
it'll stay like this if you change the density, right?
No, if you lower the density, if you increase the density, it stays. If you lower the density enough, at finite temperatures, eventually it melts because you get outside of the range.
No, assume zero temperature.
Okay, then it's just that. That's it.
It stays there.
Yeah.
Okay. Thank you.
Okay, so, but this does state that perhaps you can have some systems that aren't this exact system, but look something like it. Perhaps you have one vortex length scale, and then another one, and then it goes to zero rapidly. And in fact, and unfortunately, I don't understand exactly how this works, why the interaction is like this. But the interaction they state here is that when the electrons are close enough, you get a repulsive interaction. But once they sort of get outside of their range, then the interaction goes quickly to zero. So the potential looks basically something like this. So you have the step in it, and then of course if they get too close together, then it gets really. So this is the interaction they think happens for the electrons in these quantum pulses, and that doesn't look that different from what we just saw before. And so these are your length scales. You have one here and another one here. And unfortunately, Herb Fertig left last week. He could tell me why exactly the interaction looks like that. I don't. We were talking yesterday about it, but it is a similar interaction. So if someone can think of a vortex system in say Bose-Einstein condensation or standard superconductor where you don't have intrinsic attraction, but maybe you can get some multiple features in your potential, perhaps that's all you need to get some of these patterns. And I'm told recently there's some experiments at Stanford on these neckties where they see pairs of vortices occurring. And so the question is, do you really need this attraction put in, or can it just be a two-step potential? Go ahead.
I'll just comment on that experiment because I heard about it 2 weeks ago.
Uh-huh.
The pairs of vortices over there, actually if you measure the total flux, which is the flux of one vortex, it's a vortex that has kinks in it. So rather than being a straight line, it breaks at some point, shifts, continues as a straight line, breaks a few more times, etc. So that's what they think, at least, the Stanford group now thinks that these vortex pairs are.
Layered, right?
Well, not very.
Anyways, so the point is that, again, that if you can think of something that doesn't necessarily have an intrinsic attraction, but just a step in the potential, then you can get these strikes and clump statements. And since Professor Zanin is here now, I wanted to point out that a lot of these ideas for the hard condensed matter came originally from you, and then these other guys followed that. So here's the. So this is sort of the generic thing. You go from uniform, clumps, stripes, anti-clumps, and then will be uniform.
So the pattern which is called M1 and IMS, they think they both were.
Those are sort of the dual.
I think both machines were observed in niobium. Niobium film, but when you get niobium film very thin, you get M1 and.
Okay, so I'll say because there was the preprint by Helmut Brandt, right, and he shows these pictures, and you see stuff that looks like this, right?
Yeah, then when you go to thin film, you get it from
So then I asked him about it because I thought, well, if it's really long range attraction, I don't quite understand how you'll get
definitely.
those.
He doesn't. He says that it's just enough to have attraction to have a stripe, which is entirely wrong.
I don't think that's true. But then he said there's actually some demagnetization effects, which would mean, because you would have to bend all your field lines in here, which that's got to cost some energy. So there has to be.
Give you just a long range repulsion.
That I think would do it then.
Yeah. Then because in the film you have. The vortex has a very long range interaction.
So perhaps if they have some sort of intermediate range attraction, then it won't look too different from the model I'm about to show.
No, it's all repulsion.
Or just pure repulsion. Okay, well then maybe though, if it looks something like this, maybe that's what does it. And then, yes, I mentioned that the two length scale thing, but there's also some possibility for other kinds of multi-component vortex systems where you could have two length scales. For example, the one here, and you can imagine if the density of these gets high enough so that you have they're about to touch on one length scale, and on the other, perhaps you'll start to get these patterns at that range. So then I'll start to show our model. So our model is a strictly phenomenological model. We consider particles as long-range Coulomb repulsion, and we just add a phenomenological exponential attraction. So it's more complicated than the two-step model. And what it will do is it will be repulsive at long range, it's repulsive at short range, and some intermediate range, it's attractive. So if it's just long-range repulsion, we know that we will get a nice uniform triangular lattice. If we turn up the attraction quite a bit, eventually they'll collapse into a cluster, but then that cluster won't completely overlap because of the short range repulsion. So here's the interaction. So we're going to do over-damped dynamics. Well, in this part, we'll be starting off from a high temperature phase, slowly cooling down to equals 0, and looking at the states we get. Later on, we'll do the same thing, but now we'll have a rough substrate and compare what the patterns look like for the two states. So here's a system where we keep the attraction term fixed, and now we're going to increase the density from a low density to a high density. So here's our lowest density. And what you can see is that they form these little clusters, but then the clusters try to form some sort of larger scale lattice. As you increase the density of the system, the clusters start to get bigger. Again, we always see metastable states because these aren't completely ordered. Clusters get bigger and bigger.
Why don't you have bigger clusters of low density and much bigger separation among them?
So I see. So low density, you're asking why don't they just form a big cluster, right?
A bigger cluster than the ones that you have. You see, for example, but they'll be much further apart. Why not?
That is a good question. I'm not. So the tendency we see is that you have these smaller clusters. So eventually, if you go low in the field, it's just single guys.
On this picture, where is the radius of the repulsion? Where the repulsion sets in?
Oh, the repulsion sets in, so it's somewhat beyond, so the system size is being changed in this, right? So what we do in the simulation is we keep the same number of particles, we just make the system denser. So the attraction, right, is basically the minimum in that potential is basically on the order of this diamond. okay? Then as we increase the density of the system, this inner distance, this distance that you see between the particles, that's pretty much fixed. It changes just a little bit.
You mean the size of the clump is still attractive, everything?
The size, the distance between the particles within the clump pretty much stays the same.
But if I take two particles on opposite sides of the clump, they repel or they attract each other?
That I'm
That-
not sure. I think they made, yeah, that I think it's just on the edge, right?
So that will be kind of a critical size of the
The clump,
clump.
you're right.
So then, see, again, my question, why don't you have that type of cluster in the first square?
It should be due to some energy constraint that perhaps, because if you're low density, right?
No, because it looks to me that you have only attraction, you see, in that big clump.
Within
Right.
the big clump, it's only attraction, right?
And then it looks like you'd gain more attraction if you put more particles in and make the clumps bigger.
Yeah,
Clump
but
is
you
too
still
big, they
have,
start
but,
being repulsive.
but you still have some repulsion in there as well. When you bring that other guy in, it's not entirely purely attractive, right?
Well, it depends where this turns positive, the potential is.
I would bet that maybe in the very dilute limit, the size of the cluster is determined by the length scale at which you switch from attractive to repulsive.
Right. So if we look at
So if you
Yes,
add two
right.
at the two ends,
So,
they actually
for
repel
example,
each other.
in this unit, it's 10, it's where you have to turn around, right?
yeah, exactly.
Yes, 10 or 15, whatever.
Right.
So the size of the clump, it's 10 or 15 in this unit, or 5.
No, the size of the clump does change a little bit, right?
So how big is the clump there?
That clump here is, I believe that's 10.
And that one?
About 10 again, yeah. A little bit smaller.
So you
Remember,
have
the
only
whole
attraction in
system's
that
being
case.
shrunk, right?
Okay.
Yeah.
Okay.
So Charles,
Yep.
can I make a comment here?
Sure.
So, do you still have like kinetic energy?
There's no kinetic energy.
No kinetic
right?
energy.
It's
Yeah.
only-
There's no, but later on we'll add temperature, right?
Oh, so there is no temperature here.
There's no temperature yet. So as we increase the density, you have your clumps, and eventually you go over to a regime where they start forming the stripes. Then the stripes can get somewhat fatter, they can get, so in our case you can see they try to form a sub-triangular lattice within the stripe. And eventually they'll try to get to 4 rows, and so on.
So why do they turn? Is it-
Oh, okay, so you have to realize in this system box, right, there's only what, 5 or 6 stripes, so it's going to be affected by the boundary conditions. So that probably determines the fact that it's even ordered, and if it rains, so you're increasing the density of the system, so by going this way, maybe you can keep 6 stripes instead of having to add a 7th one.
Is it a square box or,
The square box.
so then what's the difference between X and Y?
There isn't, right? So then eventually you can see the number of stripes is less now, and you have like something with 4 stripes. Then as you increase the density further, then you get to the bubble phase. And then the bubble phase, persistent bubbles try to form this triangular lattice again. And then eventually you'll get to this uniform phase. When you finally pack it in enough, that's it. It's all, you've gone in close to the repulsive core too much, and you get back to the triangle lattice. This is a measure of the minimum distance between nearest neighbors. And this is the density. So initially you start off in these clump phases, you increase the density, so the average density gets smaller and smaller. Then it jumps up when you go to the stripe phase. The gravity starts to shrink. It jumps up again, and you go to anti-clump phase, and it jumps up into the uniform phase. And then that's it. Okay, so one thing that they emphasize is even though our potential had long-range repulsion, and we put in a short-range attraction, It's essentially the same features that you see in this model with just pure repulsion.
So
So,
it's basically like a van der Waals system.
yeah, but van der Waals doesn't have long-range repulsion.
Right.
So,
The inverse.
so the next question you go, well, how do these things melt? People haven't studied this so much. So this ordered stripe phase, sort of the first state we'll start off with, because you can have well-defined diffusion in one direction versus another. So these are the positions of the particles. We trace out the trajectories over time. So at a low temperature, it pretty much stays solid. But at a higher temperature, you can see it starts to essentially liquefy along the stripe. So if you can watch a particle, it will actually move along stripes. But you don't see any hopping across stripes until a higher temperature. Then you can get stripe to stripe hopping, but the stripe structure still remains. And then eventually the whole stripe structure itself melts. And I'll jump over this. If you look at the specific heat of this system, is when the stripe structure itself melts, you get this nice fat peak. This is just the fluctuations in energy. So here's again the peak coinciding with the same peak you see in a temperature. And there's some shoulder signature you see here, and that's actually within this phase. So if you look at the diffusion, so this is diffusion in the x and y direction, this is time. The low temperature phase, this phase here, it's still somewhat anisotropic, but it's subdiffusion. It's not. It seems to be balanced.
Can you show the specific heat again?
Sure. Oops. I wouldn't read too much into this. But you see there's some, so at a relatively low temperature, you start getting diffusion along the stripe. So there seems to be some actual feature here. I wouldn't say it's a phase transition. This looks, I would say this is probably consistent with the first order phase transition. So then, now when you get into the a little bit higher temperature here, so this is A is here, B is here in this temperature, is that you get the diffusion is bounded in the across the stripes, but in the y direction it's unbounded. It can keep going. Then at higher temperature, still say C, you still have stripes, but you have particle hopping across the stripes, so it's anisotropic diffusion. And then finally, at D, once it melts, your system becomes isotropic.
So you would like to call it a symmetric?
So these, I would say these are symmetrics, right? Yeah.
So was skips pneumatics, right?
We don't. I mean, the thing is, we can't rule out a pneumatic phase. That there could be a pneumatic phase because our system's too small. Because if there was a pneumatic phase, you could imagine these two. There could be a dislocation, but perhaps you would need a few hundred of these stripes, and then you could see a pneumatic phase kick in. So we can't rule it out, but within our system size, we don't see it. But it's definitely a region where you can see the structure itself break up. But yeah, you might think maybe a pneumatic kicks in here, right? That, at some point, maybe a dislocation in the stripe pattern itself comes in. So here's again, you see nice specific heat signature. So what happens if you go to the bubble phase, or the clump phase? Is you see something somewhat similar, but because they're not connected, you end up getting a liquid phase where it's liquid-like within the droplets, but there's no particle hopping out of the droplets. At higher temperatures, you can get activation out of the droplets. The stripe structure remains, the clump structure, lattice structure remains, and eventually the thing melts. Similarly, if you go to the inverse of that, you get a phase where it becomes liquid-like throughout the structure, but the lattice itself, holes remain, eventually the whole thing melts. And I should emphasize what I didn't have include the plot here. that if you were to sort of trace out the onset of this peak, if you do a series of simulations and you look where this peak occurs, it's a function of temperature, you get a dome. Like this, and actually goes back up once you get in uniform phase. So at low densities, you know, it's not very well ordered. But in other words, the stripe phase, this transition is the highest temperature. And then it dips down again, and then it goes back up when you get it in a really packed phase.
Sorry, I didn't understand what's on the axis now.
This is density, and this is Tm or Tp, which is the peak in the specific heat. So its maximum, the highest temperature you see it is within the stripe phase. So what I showed you is just the genetic model. More recently, we are trying to, since we're interested in working on these 1.5 superconductors, is trying to think of a way to do this for a vortex system. And one of the ways might be by putting looking at a magnetic superconductor. So what happens is you have the vortex in a magnetic media that causes a distortion in the magnetic media, which the vortices can reduce that magnetic distortion energy by coming together. So your pair interaction, this is the standard repulsive pair interaction for the vortex lattice. But this is the attractive term mediated by the susceptibility. So you have something that has a long range attraction. And so
Why is it? Oh, sorry.
okay, go ahead, Mike. No. Okay. So here's essentially the same type of simulation, and I'll say a few things about these. But one, we don't see stripes. I mean, this is sort of a stripe, but I wouldn't read too much into that. And as you increase size some levels that are far too high for any real material, you start seeing the bubbles. And you can ask, well, why doesn't it form one giant bubble if it's really long-range attraction? And that's because when we do the simulation, we cut off our interaction at about 10 lambda. We say beyond 10 lambda, all the forces are zero. And so these clumps form, and they're actually outside of the range, so they just don't feel each other. In reality, if there was a long-range attraction, perhaps that would, bring them together. Or if you put a temperature on it, these things will thermally wander around, and eventually they'll get close enough to the attractive corona and the clumps. So I think in general, a system with long-range attractions, the lowest energy states are just a big clump. However, and we'll get to this other part, it's possible though that there's always quench disorder in these systems. So in other words, here's the bubble phase I showed you before, without any kind of randomness in the substrate. But if you put randomness in the substrate, which could be from pinning, it has a tendency to break this up. So even if you had a system with long-range attraction, if you have disorder in the sample, perhaps you're going to see something inhomogeneous.
Even if you don't have attraction, you might have that.
Of course, yeah, okay, yes. So how might you be able to probe these systems? So here's that clump system I told you that has that's pinned, and it's broken up. Now suppose you apply a current or shaking thing or something to the system, it starts to depin, and then once it gets into the moving state, it's able to sort of dynamically smooth out the rough substrate, and then the moving state will be able to reorder back into something that looks like the equilibrium state without quench disorder. And you can do the similar thing with the stripes. Like if you have a lot of pinning, your stripes are just destroyed. It's inhomogeneous, and this is the structure factor. Of course, you still have two rings because there's still two intrinsic length scales in the system. You drive it, and then in the moving state, you can form the stripes. In addition, the stripes are ordered with the direction of the drive. So the basic idea, suppose you have these 1.5 superconductors that Victor has, we think if he shook his system back and forth or drove it somehow, if it's really this long-range attraction like he says, then you should start to see the system become more clumpy dynamically, if that's the case. Another thing that these stripe systems, or these pattern-forming systems do, is if you look at the transport, is they generally have lots of hysteresis. So this is an external drive, this is the average velocity of the particles, and this is in the stripe phase. And it's pinned at first, and then becomes unpinned, goes eventually the high-driven phase, where they form the stripes again, you lower the drive, and the stripes persist for a longer time down as you lower the drive, and then they break up again. In other words, so the system will stay in this longer as you go down. And one way that we think this might be true is because we think these systems generally have first-order phase transitions between ordered and disordered. And there's some evidence, for instance, in the quantum Hall systems, there's some evidence that you do see anisotropic, where you see anisotropic transport, but you see hysteresis in the transport curves. Now I know certain vortex systems without attraction or anything will also see hysteresis in the IV curves near the disorder order transition, so it's somewhat got to be skeptical. However, our claim will be that if these systems are, you really do have these clump-forming systems, they'll be hysteretic over a much wider range. So remember I told you that there was a dome in the melting temperature versus density. If you do these simulations where you start off uniform here, it's uniform here, and stripe right in the middle, and you look where the hysteresis occurs in your transport curves, you see that it's highly hysteretic within this range, and it's most hysteretic within the stripe phase. So here's a low density phase with pinning, high density phase with pinning. Those don't produce hysteresis in the transport curves. They look very similar to what we do simulations of vortex systems. It's just pure repulsion. But within the stripe and clump phases, you always see some kind of hysteresis.
How does this relate to sliding charge density wave systems? They are usually non-hysteretic, right?
Non-hysteretic is what
Yeah.
you're saying.
What is different here?
So what's different? So okay, so the sliding charge density wave system, that's just the simplest model might be something like a frontal controller model, right? So that would look more like, I would say, look more like this system with just one length scale. And the one length scale systems don't have hysteresis, but the two length scale systems do, because the length scales are mixed in the pin phase, but they demix in the moving phase. And that's when you get only one length scale in the moving phase. It persists for a while, then the disorder mixes it again. So, I mean, it is a sliding pinning type dynamic. So perhaps in these 1.5 superconductors, they can see if they're really much more hysteretic than the standard superconductors. And also, if they can do imaging, perhaps they can just see that you can get, more ordered states in the moving phase. Okay, so now we're going to go back to some fun stuff in a few movies, because Alex says no matter how bad your talk is, if you have a few movies, people like it. This idea of stripe and cone formation also, actually, for Professor Zanin, I believe was sort of proposed for physics of nuclei, where what is the repulsion? Protons. Where is the attraction? Is actually the strong force. And Professor Watanabe, I believe, is going to be here next week. The same guy, I think.
Yeah.
So here's a
This
simulation.
is neutral stars, right?
Yeah.
Neutron stars, yeah. So this is for what they call pasta phase. And by pasta, they don't mean oolong pasta, the mathematician. They mean pasta, like spaghetti. And so here's an example of what they call quantum molecular dynamics simulation of neutrons and protons. So the protons are repulsive, but the neutrons mediate the attraction. And you see they get very similar phases to what we saw. Is you get bubbles. They also get the anti-bubbles. They've done three-dimensional simulations where you get even more phases. And in fact, they also look at the melting transition, and he sees the same dome where stripes or slabs are. That will be the highest melting temperature. So this sort of says that, you know, despite a wide range of interactions, you get these generic phases. And so where would you see these? As mentioned, neutron stars. So you need to get the stuff dense enough for the strong force to come into play.
So that picture was a simulation
That's it's a
with the standard model with QCD.
no, they call it
That's not
quantum
there.
molecular dynamics. My friends at Los Alamos say it's really just molecular dynamics.
Yeah, it's molecular dynamics. Really.
Yeah.
This is like a high temperature limit. Temperatures larger than the degeneracy temperature for an energy.
No.
Well, it's an approximation that some people.
It's very unrealistic in that respect. The temperature, the critical, I mean the Fermi energy, it's about 30 MeV. So this is 1 MeV. So this is the general system. So you cannot do molecular dynamics really. But you can make some arguments that you can do this type of simulation, but well.
Okay,
Anyway.
So is that
Some
actually,
people make a living.
so actually it's a low temperature for a high. So the permitting is much higher.
This is a degenerate system, quantum degenerate system at that temperature. So you cannot do classical simulation really. But
They do.
yeah.
So anyway, so where you might
Much
see
more.
these things would be in a neutron star where you have the Coulomb crystal when they're outside of the strong force attraction. Then when you start getting on the edge, you start getting these pasta phases like spaghetti, and eventually they get close enough, you get into a uniform phase. And so how does this relate to some of our things? So we were looking at the same system I showed you before, but we go to a limit where it's strongly, the attraction's strong, so they come close together, and then we gradually turn up the temperature and see how the system would melt. And the first thing we noticed is that they have a tendency to fluctuate more on the edge. So you can ask, how do you think the system would melt? You can see them fluctuating on the edge, and then eventually what will happen, these are two different seeds. So this thing, it doesn't just evaporate, it undergoes a fizzing-like instability. So this is good for justifying funding at Los Alamos. But there's a few things you also might notice about this is no matter how many times we do it, there's a tendency for it always to be asymmetric, that you get a big drop and a smaller drop, and there's always one guy who can't decide quite which thing to get in. It's not a neutron. There's no neutrons in our system.
So what's the difference in particle numbers in these two fragments? Are they?
It's an integer number.
It is an integer, but so you must show where they have the plot here, right? But you get a distribution that's asymmetric, and we are thinking the reason why you get that, if you notice when it was melting, there was some fluctuations on the edge, right? So if you assume sort of like there's an entropy associated with the perimeter of this, you can ask when would that be maximized? So if it splits exactly in two pieces, that's lower than if it splits in a bigger piece and a smaller piece. But it's not as low. I mean, it would be much lower if you had just one giant piece and one little piece. So when I showed this to some colleagues at Los Alamos, they thought that it was kind of cute because it's known as something called the fragmentation asymmetry in real nuclei that you see. And this is, I'm sure you know Schmidt, is that this is, if you see giant nuclei break up, you don't see them break up in equal pieces. They always break up in a big piece and a small piece. And depending on who you ask, they say that this isn't really well known, or it could be well known, but it's not intuitively clear what's going on. But perhaps it really has something to do with fluctuations on the surface, and there's just a lot more ways to break up into an asymmetric piece than a symmetric piece. Okay, so that was a cute thing that I wanted to show. Maybe I'll skip this since we have time.
Since you mentioned the pasta phase,
Yeah.
if I'm not wrong, that was predicted first time in the early 70s by one of the co-organizers of this program, Chris Pethick, Bain,
Mm-hmm.
and Bete.
Mm-hmm.
So,
So, the organizers of
Chris Pethick, it's one of the
The Morbido?
co-organizers of this program. Yeah,
Okay, very nice.
yeah.
Okay.
So, but that was done in the early 70s.
Uh-huh.
So Hans Bete, okay, and Bain and Pethick did that.
So yeah, we saw this earlier. So I'll finish off with
And
one
in
more.
complete different arguments, you see, and
Yeah.
those are much, anyway, solid.
I missed it, anyways. So I'll finish off with, again, a movie is that I told you earlier how you can get traction in equilibrium with just purely repulsion, but suppose you have a system again with just nothing but repulsion, and this time it's just Yukawa interacting particles. So all the particles have Yukawa repulsion. We'll pick a few guys that have a little bit more Yukawa repulsion, and then we'll couple them to an external drive, but not couple the rest of the particles. So only those particles will move. So there's periodic boundary conditions in the x and y direction, and the drive will be in the y direction.
When you say drive, what exactly do you?
So this is overdamp dynamics. So this red guy has a constant force on him.
Okay.
And it's a binary distribution, that's why it didn't crystallize. And so they're moving, you can see they're trying to, they're pushing the other guys out of the way that aren't driven. But over time, you'll notice something funny is that they have a tendency to attract one another, even though all the pairwise interactions are repulsive. And occasionally you can see that a blue guy gets entrained between two red guys, is dragged along with them. And then if we wait just a little bit longer, go ahead.
Can I think of this as the fact that you need to push away some of the blue balls, that makes the blue ball background like an elastic sheet?
You got it. It's
And that's
exactly,
the effect of
it's
attraction?
that's what it is, yeah.
Okay.
So this is neat. So now these guys are paired up, right?
Oh yeah, and you get little trains.
Yeah, you get trained. So the other, and then they can move faster because the other guys,
Yeah. Oh yeah.
yeah, they get longer and longer. But it's disordered, so occasionally a guy will fall off in the end. So as you said, it's like pushing through an elastic sheet and causing a distortion. Another guy's causing a distortion, but they come together, they share the
So it's a root
distortion.
temperature superconductivity.
No.
Well, no, because I mean,
Pair channel is not
There is
protected.
drive, external drive. there.
Basically, it's flawed and it's got tuned for BCS theory and phonos just to require.
so the other way, I mean, it's also known if these were people, for instance, if you go to an airport, there's lanes that form, and they just sort of naturally form, and you end up going
Where if you go to Border France.
Yeah, there was like
Oh, yeah.
experiments. There were experiments there were people were put. Do you know about these experiments? Exactly this. So psychology that put large number of people in a room and instructed very. I should remember exactly experimental setup, but there was something.
to leave the room. Or
If it's people, it's not an experiment.
Two kinds of people and.
So anyway, so this just shows that you can. This is another way to get traction.
So is the temperature here?
There's no temperature. So,
Crowd dynamics.
there is such a thing as crowd dynamics.
Yeah.
In fact, I know Dirk Helbing is a physicist, but he gets lots of money from transportation companies, where they do simulations that aren't that dissimilar to this, to look at how crowds will exit. Suppose this is a box, and you have a hole here,
Yeah.
and you instruct particles to move through, how they move through, and it's particularly important during fires because there's a jamming transition at the door, everyone will die, right?
Yeah, that was like in Duisburg the other day, right? That was basically
So
this
they
was a
try
Dutch
to design
newspaper. The
these-
physicists were kind of figuring out
Yeah,
how to avoid that people die in crowds.
yeah.
Hypothesis.
Oh, in Germany,
Perfect
yeah.
crowd.
Yeah, the one anyways. And you can also add panic by just adding something like random noise.
Yeah,
And then, so,
Yeah, it was like a magic number. I think that when you have more than 5 people per square meter, you have basically get very susceptible to panic.
panic, I
Dying.
see, yeah.
Right? And when you have like 3, it's fine. In Duisburg they had 10.
10, I see,
Yeah.
yeah.
It was all in Dutch newspapers referring to physicists' work.
I wonder if it was Dirk Helping.
Feltus.
Yeah, that might probably be that guy, right? Anyways, were they in a tunnel or something, I believe, where they
Yeah.
constrained
It
geometry?
was just very high density of people in the
Yeah.
crowd doing it.
Anyway, so, we're going to the end here, so we saw, I mean, it wasn't just pure attraction, but if you have some combination of competing interactions, maybe short-range attraction and long-range repulsion, you'll get this very generic set of phases, the crystal, clump, stripes, anti-clump, so on. The other thing, the important thing, is that you can get these phases with just purely repulsion. So if someone has a nice pairwise interaction they think could exist for a vortex system or a charge ordering system, we would like to simulate it. We have the justification for it. And perhaps this stuff's also going on these type 1.5 superconductors. To try to show you quench disorder generally distorts these phases, so it gets very hard to understand if they're there. But perhaps with dynamics, by shaking it, you'll be able to see the underlying phases and so on. And again, I'll just thank the organizers for letting me come give a talk. Thank you very much. Thank you very much.
Questions?
Just one comment, since you're talking about the competing interaction between two vortices. Actually, I'm very surprised they noticed our work on in a different system by Jan Beck came to me on this superfluidity charge
I'm
neutral.
sorry, I didn't mention it.
You do mention, yeah. I'm very surprised they noticed that what we have done because it's on different system, right? But actually, I just want to mention that you had a model with an attractive interaction in the shorter range, but in a long distance repulsive, right? So over there in this cold-adding system with strongly interacting Fermi gas, on the BEC side, actually people really have not really done experiments on that because people think it's boring. So you have a phase, it's like a polarized uniform superfluid, where inside the superfluid you have a Fermi surface. And so you indeed have a kind of a competing interaction between two vortices because you have the conventional coolant. And what we realize, you have there's some particular polarization regime. You can have a Fermi-induced, basically the Fermi surface in the middle, like RQQY type possibly. So you could have a shorter range repulsive, and in the intermediate region you have a attractive. In the very long range, you have repulsive.
Yeah, so if that's...
that actually may... I mean, I think it's very viable to really realize in the
that sounds
cold-adding
almost
system.
exactly to what our system was, right? So
So you had a...
you would so yeah, I mean, that's
So
it's almost like
those
this.
phases may well...
Yeah,
So unfortunately, in our case, we don't have analytical formula for the potential. It's very complicated. So we don't have a plot.
If
So-
you can get that, if you just have a numerical,
We only have
get the
numerical.
numbers, right?
Yeah, so only have we don't have, it's very difficult to really get the analytical solution to this. But if I look at the structure,
Yeah.
I think qualitatively have all the...
And no one's done any experiments in that regime.
Because I think, people think, this resonance regime is interesting. For that window, people feel, that it's not really exciting for the moment if you point out like this.
Maybe they'll
We actually speculate a little bit, but I don't think people... I mean, if you really have a more theoretical prediction of new phases, like say novel structure of like a vortices other than the kind of a transitional triangle lines.
Yeah, exactly.
And the
There-
people
there
can
might
really
be-
see the vortices, right? I mean, they can already see the vortices without any problem. But the question is, are they willing to do that on the
On the-
regime where this polarized uniform phase, people also call it like BP1 phase, with one Fermi surface.
Well, if you can, even if you just can get me you don't have to get an analytic solution, but if you
Yeah.
can get a numerical
So
thing,
we can talk more.
you can put that actually just in a simulation,
Yeah.
right? You just need a table, you don't actually know the function.
Yeah. Actually, it's related to Igor's early work.
Yeah,
on-
exactly.
I think it's related, right?
Hmm?
It's related to the like
Yes, yeah, we-
two-component
We
superconductor.
actually also can get short-range attraction or long-range repulsion, and also like turning it several times from repulsion.
So with the code, and of course, one of the advantages you can tune the polarization,
Mhm.
tune the density. So let's say
You can see the
you have
phases.
some freedom. You have
Yeah.
some freedom to go in different. So for example, you can change the location of the minima. Of the,
Yeah, exactly, I see,
yeah.
right.
So that means you may drive the system to different phases
Mhm.
for the vortices, right?
Mhm,
By
yeah.
changing the polarization.
You can see how metastable they are too.
Yeah.
Once you get in a pattern and you change the interaction,
Yeah.
does that persist or does it have some instability?
But so far, no one has done any numerical calculation for the vortices in other region.
Right.
So I have some question about stripes in general. So in solid state physics we are used to that these stripe phases usually require some quantum regime to be realized. However, they are good realization since they exist in quite some materials. And so my question is actually how much of these quantum phases in nature do you think you can explain with these classical simulations? There's some simple, intuitive way. I mean, you had this long-range repulsive interaction plus short-range attractive. It seems rather in the quantum machine you find these phases in nature.
Perhaps I can comment quickly too. I mean, it has been, I guess, one of these ideological fights that were never fought out openly between, say, what Steve Giffordson was promoting, which was basically this picture of competing interactions. And I was always more on the quantum side, that in order to, say, explain really what's going on with these electrons on the ladder scale, you know, h bar is pretty important, and there's really a bit more going on than just this classical interaction bit. So my answer would be that to really understand what these Sherman-Davis pictures are, this is a bit oversimplified.
Right. Well,
It's absolutely not oversimplified, you know, when you really go into these applications that you are addressing.
So, I mean, he has a good point. As I said, I showed some pictures of Shaman Davis just to say there's some interest, but I'm not going to say anything about it, right? So it depends on what kind of phenomena you're trying to explain, right? I mean, if you can capture something, some simple parts of the system classically, then that's good, even though, of course, these models never explain all the behavior of the quantum Hall systems or the high temperature superconductors. But for example, in this thing here, we have a system with this order. You apply a drive, and then the stripes order with the drive. There's some evidence by the group in Stuttgart that that's exactly what they saw, because they see hysteresis and they see the stripe. Which you order them one way, then the anisotropic direction changes. So that seems to be sort of capturing some general behavior there, even though we don't have any quantum mechanics.
But this makes me think, I wonder whether you are aware that this a number of years ago, I just know it because Peter Kess in Leiden was doing these experiments with driven vortex lattices, and you exactly saw this kind of channel formation.
No, but he
Yeah.
had a trench for vortices.
Yeah.
He had a trench, specially made trench. So
Well, he has
Yeah,
So
but it was just to have a lot of
Right,
current
right,
going
yeah,
through, and then he made
no, but-
movies of how they were
yeah,
moving.
yeah.
And exactly this
Yeah,
kind
yeah,
of
so
spontaneous
if
pattern
you have a
formation.
single channel,
So
then
that's
you have a lot of plastic, elastic.
yeah. So you could
just
imagine
dragging
doing
vortices.
something like if they could etch their samples, you could put a pattern on it. You could start doing
Yeah.
the stuff like Peter Kess.
Yeah. Or you just have a grain boundary.
Peter Kess does, right? Yeah.
No, in general.
Yeah. I mean, Peter Kess also did some work where they just took there was no channels. They just drove it, and you
Yeah.
see the vortex lattice starts to align in the direction
Oh, yeah, that's well known, that's, that is.
Yeah, because my background actually is in vortices, and that's why we thought, well, maybe some of those ideas could be applied here, that's how we got into it.
Actually, you don't have this effect here, because that requires taking into account the word score, like there is a little tail, an equilibrium tail coming out of the core, and the next guy feels this tail, so they get along.
Okay, that's like a real droplet, right?
No, it's because you have to take time-dependent Giesbrecht out to get that.
So the only argument I can say against the time-dependent Landau stuff is it's very hard to do a simulation that would see all these dynamical phases. I mean, ideally you'd want to do those things, but as you saw, you only get one or two vortices. So this is just a different approach that sort of looks at a different one.
That's one more remark. So these stripes, bookways and so forth have a long history, and I guess we kind of agreed at the point that this business of the competing interactions is sort of more of a necessary than a sufficient condition, right? That, when in the classical limit you wouldn't have this tendency to form these patterns, where you feed it in whatever way with the lattice in H bar, it might not happen. It's basically saying that there is kind of a domination of potential energy, but the kinetic energy is of course of relevance, measured at microscopic scales.
So this was this the original paper where you mentioned some of this?
Yeah, there it started, yeah. And this didn't really know about this competition, right? It was just the, we called it stripes actually in analogy with the formation of discommensuration lattices, incommensurate systems, right?
Oh,
Where
I
the
see,
modulus
I see.
is like the commensuration
So it's like
physics.
the domain walls.
Yeah, so it's basically like this is associated with
Yeah.
the fact that you have a mod insulator that you don't, right? And the mod state is very stable because it's a commensurate electron density wave on top of a
I see.
commensurate potential, right? And then you dope it, and then this electron crystal wants to change its lattice constant.
Mm-hmm.
And
So
when the
it's
Ookla
like
is
a
strong, you
2D
form these
Fractal
commensurations.
control model that
Yeah,
has,
exactly.
that doesn't fit in but forms,
Yeah. And that's more like coming from, say, doing the microscopic Hartree-Fock calculation, in essence work that way. And I guess all these TJ model calculations and so forth later on are basically reflecting that kind of morale.
Mm-hmm.
Although in reality the stripes are more stable than you perhaps would expect, right? And then these other motifs of long-range detection and so forth.
Well, one thing
Have
that
to be cared
I've
about.
always wondered about these high temperature systems is, in this case, sort of the background lattice is utterly fixed. But what happens if there's some little local strains caused by the in the system? Then that might stabilize some of these patterns as well.
Yeah, I would say for these kind of hard stripes, it's perhaps less important, but when you go more into this sort of more subtle phase separation business,
Yeah.
you have, basically when you don't see really these hard stripes so much, then I think that's very important.
Mm-hmm.
I'm just back from a meeting in Ericshay dedicated to homogeneity, and these strains are prime suspects
Oh, really?
for
Right, yeah.
giving extra effects.
Because I know just
Homogeneity.
people who do just strain crystals also see stripes
Yeah.
on their own, right?
Yeah.
Questions? Thanks to the